I would like to start off with a little bit of a motivation why we need this kind of approach before I go into detail on what exactly this is. So what we try to do is design. So basically find some molecule, find some system that has a certain desirable property. And the problem is that this is an awful search problem. And the main reason for that is just the sheer size, which for many cases is measured in powers of 10, which is not good. So imagine you're looking for some pain medication, and the first question is, first you need some kind of molecule that has this effect of reducing the pain you feel. And you can consider this to be a global search problem, if you do this from a clean slate. So that's the kind of left, and there's a common estimate that it's about 10 to the 60 drug-like compounds that you can look at. And once you've found one, once you've identified one, now you want to refine it, locally optimize it, such that now it's more effective. And that's a local search problem. I brought you another example. So consider a small surface, an 8x8 graphene unit cell, and you n-dope that. And then the number of spatially unique ways of doing that is about 10 to the 50. And the problem with those numbers is that you can't even afford to enumerate any of this. Even if you just have to generate these things, it's too expensive. Not even you can't even calculate them. So what we need is something that goes away from doing things one by one, but rather can look at groups of systems of molecules at once. And we heard a lot in earlier talks on machine learning, how to do that, the data-driven approach on that. But I would like to talk about quantum alchemy, a little bit a different approach, where the idea is, instead of the machine learning approach, where you have individual points that you calculate with your favorite quantum chemistry method, and then you use a statistical model to infer some compound that is within those points that you found. The idea with quantum alchemy is you know one compound very well. Most importantly, you know how its energy or other properties change as you change the nuclear charges of that particular compound. So it's the local gradient in chemical space as you change the structure of your molecule. And there's a reason for this, why these directions are orthogonal to each other. Imagine you have a compound and you can now replace one atom with a different element. You can replace a second atom with a different element. And those are independent changes that you can make to the molecular structure. Now, I would like to suggest to treat that perturbatively. And you will say, what? Perturbations is usually something small. And you take one element, you put another element there and claim that's small. No, it isn't, but you can still get accurate results with this. And I will show you some examples. So the nice thing about it is it's a Taylor expansion. So as long as it converges, we can systematically improve by adding higher orders. And that's what I mean in the title with systematically improvable models. Now, of course, there is still a catch. It's not like you can do one quantum chemistry calculation, which then is the last quantum chemistry calculation ever, and you just perturb to whatever target. That doesn't work. So you have a finite radius in chemical space that you can access. But still the point is that within this volume that you can access, there's very many systems, and I will show some numerical results for this. So let me show one example why this would be helpful. So imagine you have a chemical space, and every point in there, so those points are supposed to be the chemical space, and every point is a system, is a molecule. Now, what you can do, in the traditional sense, is you can calculate a few of those. That's what you have on the left. The orange larger blobs is what you actually calculated explicitly. And now you can find some interpolation schemes, some statistical procedures, machine learning, whatever, in order to fill the gaps. But in the perturbation picture, you not only get the points in chemical space, you get information about a certain area in chemical space. It's approximate, yes, but it's with workable accuracy. And I will show how that works. So you not only get individual points, but you also get a certain range around them that can be covered. So the idea is if you ever look at some large-scale calculation or high-throughput screening, then if your system lends itself to this kind of treatment, then that might be a clever way to not do some intermediate level quantum chemistry calculation that you can pay for all those different systems, but rather do fewer high-quality calculations and then treat the molecules nearby perturbatively. Now, which things do you want to perturb? I mean, molecular Hamiltonian takes some nuclear charges, some positions, the number of electrons, and the spin. And for all I'm going to discuss today, I'm not going to change the number of electrons, and I'm also not going to change the spin. Why is that? Because that's a 1D problem, effectively. You can just enumerate this. You can do the perturbations for this many electrons, for that many electrons. That's only one dimension in terms of the search space. That's completely different if you look at the nuclear charges and the positions, because, of course, all possible combinations of those changes, they just give this combinatorial explosion. So that's the hard part. That's why we care about that. And we have heard in this particular workshop some nice argument why the number of electrons should always be, not only in practice, but also in terms of stability, be close to the total sum of nuclear charges. All right. Now, how do we do this from a practical point of view? You probably have guessed it. It's a Taylor expansion. You already know and use derivatives of, say, the total energy with respect to changes in geometry. That's the forces for geometry optimization, or in the second order derivative, that's what you use for vibrations. So this is very well established. For some strange reason, nuclear charge derivatives haven't been explored much. And those are the alchemical changes. So that's all perfectly fine. Schrödinger's equation is valid, whether your nuclear charge is integer or not. So just because we can't make them in the lab doesn't mean the equation doesn't work. It's just a change in the external potential, effectively, that acts on the electrons. So the idea is you take one compound, you calculate it, and now you also obtain the derivatives in some direction in chemical space. And then the hope is that the leading orders carry the dominant information of that. So since you probably have never seen those derivatives, I brought you some example. So this is benzene, or more precisely, the electron density of benzene. And what we want to do is we want to change benzene to this molecule right next to it, so to a Bn and B doping pattern on the ring. We keep everything else fixed. Geometry is the same. We just change the nuclear charges. And now, this is one direction in chemical space, so I can calculate the derivative in that direction. And the zeroth order derivative is just this electron density of benzene, where I come from. And this is how the first order derivative looks like, and the second and the third. So you see that the symmetry, of course, of this change is reflected. But the beauty of it is, as you add them together, you approach and approximate the electron density and the corresponding energy of that particular molecule in that particular geometry. Yeah?
Can I ask a quick question? Is there some underlying hypothesis of like analyticity or something like this? That if you change the nuclear degrees of freedom, or the charge, and you would calculate it exactly, that there's some like, there's no level crossings, right?
There's very few hard guarantees in this. Ebrard Wilson has proposed, I think is the oldest paper I know of in this direction. It goes a little bit in the spirit of this adiabatic connection going smoothly between molecules, but that's non-perturbatively. That's actually going the full path. I'm not aware of any rigorous proof that this will exactly converge, except for very special cases like free atoms, hydrogen-like atom. There you can show a pen and paper. But general case, there's numerical evidence. That's going to be one of the slides later. Okay, so how do we do this? Well, it starts a little bit in the spirit of this adiabatic connection. So you take a molecular Hamiltonian, the one where you come from, that's the reference. And you take the molecular Hamiltonian of the molecule you're going to, the target. You linearly interpolate, so if lambda is 0, you at the reference, benzene in our example, and at lambda is 1, you are at the target, so the BN-doped benzene. Now what you can do is you can do a Taylor expansion of the energy of that new mixed interpolated Hamiltonian. And it's important to note that in all of that, you only ever use derivatives evaluated at lambda as 0. So all derivatives are evaluated for the reference molecule. There's no quantum chemistry calculation or no density information required for the actual target. Now, you can use Hellman-Feynman and exploit the fact that those two Hamiltonians differ exactly only in the external potential, which is a nice thing to evaluate. So what you have is your first order derivative is the change in nuclear interaction, which I will ignore for the rest of the talk because that's the boring, trivial part that can be calculated classically. And then we have just the integral in space over the change in external potential times the electron density. Now you can continue to do higher order derivatives, and what you end up with is this equation. So that's just the Taylor expansion. You get the energy of your target, function from the energy of your reference, this molecule that you know really well now, the change in nuclear interaction, and all the density derivatives. You can also cast this in terms of energy derivatives. There's different ways how you can phrase the same thing, but the core idea is, in this case, to use the density derivatives because then you can use them to also build the density of the target, of the target system. Yeah, Gil.
So are you varying the number of electrons as well? Because you no, but how do you model this, right? Because the thing on the other side should have more electrons, not just higher nuclear charges, right?
No. So if I be n-doped, then I wouldn't change any.
You're not. I see. You're only doing fixed number.
No. So exactly. So the idea is that there's maybe for a given set, there's maybe 3 or 4 total number of electrons that actually matter. So if you have a design problem, then you can just do the perturbation with that number of electrons and this number of electrons. That's maybe add a factor of 2, but it's not gonna scale combinatorially and change the complexity of the problem.
Do you expect the series to be convergent or only asymptotic? Is it an asymptotic series?
I will show some examples for that. But thank you. I always get this question. That's why we looked at the numbers. All right. So the idea is calculate those derivatives and then piece things together. And then you can use the same derivatives for getting energies, for getting the density, or for getting, of course, any one-electron property, because if I have the density, then I have those as well. All right, now the question of convergence. Actually, if you want to try this out with your favorite quantum chemistry code, there's some playground, or ask me. Okay, so the question, does that converge? And this is something we looked at. So if you focus on the left plot for a moment. So the idea is the following. You go either from the N2 dimer to carbon monoxide, or the other way around. Those are 2 alchemical changes that I can do. So you can only evaluate, say, N2 dimer with your favorite quantum chemistry method and all those derivatives. Now, I'm not proposing to do 40th order derivatives, but I want to show that this actually keeps converging. So here you start off with in 0th order, of course, with the energy of the other molecule, and then as you add more and more derivatives, this becomes more accurate. So very quickly you reach chemical accuracy. There's 1 kcal per mole common threshold. But the fun thing is it keeps going. So this line here is the typical SCF convergence, where if you were to do your self-consistent calculation on the target molecule, this is where you would stop. You would say this is good enough. But in fact, if you can work with this precision, then the series itself would just keep going in terms of convergence. So the idea is, of course, truncate very early, because 40th order derivatives are just going to be unwieldy and too expensive. Now, the one thing is that it does converge, but the other question is, does it also converge to the right value? Sorry, there was a question? Okay. It also converges to the right value. And here is one example where we evaluated that for different directions. So imagine this is a dimer again, and you have the nuclear charge of 7, 7. So that's N2. That's the reference, this red dot in the center. Now, every small red dot that you see is one possible molecule that you can have in terms of nuclear charges. And the lines you see, that's the convergence radius. That's how far you can go with this Taylor series, and A converge and B converge to the true self-consistent value that you would get for that particular molecule. Now, you see the chain, the radius depends on the basis sets, and I will talk about that later in a bit. That's more of a technical thing, but the key message here is you can go pretty far. So if you go from N2 to CO to BF to beryllium neon, this still converges. So it's just barely at the limit, but nonetheless, this is quite a substantial change in terms of nuclear charges that you can make. And that's what I meant initially with, yes, this is not a small perturbation, but I mean, ultimately, it would converge. In practice, with the first few orders, 3 to 4 orders, you can do plus or minus 1, sometimes plus or minus 2 in terms of nuclear charges. So this, of course, is done with a special implementation of Hartree-Fock. Might be interesting for people doing method development in Hartree-Fock, because this can do arbitrary precision. So if you, within a fixed basis set approximation, this code can give you arbitrarily many significant digits for your calculation, and that's how we got the corresponding 40th order derivatives. Okay, you can say this is a boring dimer. Some other examples I would like to mention. If you look at the top left, this is H2 to helium. So this means you have, sorry, there's a question?
Can I ask you a question on the last slide real quick?
Sorry.
Do you have a sort of rationale why the nitrogen dimer to carbon monoxide converges more quickly than when it's reversed?
So we observed this in many cases, that perturbing from the more symmetric case converges faster. So here, going from H2 to helium, or the other way around, is a funny thing, because you either create or you remove a nucleus. So you take a start from helium, and you grow a new nucleus at some distance, and treat this as a perturbation to the electron density. And this is just as an idea. The colors mean the same thing as before for the energy, but both your energy, your density matrix elements, and your orbital energies just converge for this change with higher orders. And the limit of what works is here. Another example is going from between 3 helium atoms and 6 hydrogen atoms, because a hydrogen chain is well known to form dimers if it has an even number of hydrogens. And that's what you see here. The shaded blue area is the density that you would expect. You can't see that on the projector, I'm afraid, sorry. So you would expect 3 dimers to form, and this converges, but just barely so. There's still a substantial deviation in the density shape, even in those orders. So at some point, of course, it breaks down how far you can go. But this is, of course, a crazy change. Now, the other question, besides the convergence that I often hear, is what's about geometry? Because as you change nuclear charges, geometry is going to change. And here is one example. That's going to be my only example for this talk. is going from helium to H2. So you do one calculation of helium, you know it really well, you have all the derivatives, and now you place your hydrogen atom at different distances. So you can get the bonding potential of H2 just from helium. And this is what you see here. So it's second order, you get this line, which of course is far away. Third order overshoots a little bit. And fourth order, the dashed line and the yellow line, you can't really distinguish on the plot. They're almost exactly on top of each other. So you can get the geometric response, in this case, the bonding potential just from a single atom. So what can I do with this? Give you one example. Here you see the C20 fullerene on the left. And now the thing is you can de-n-dope this fullerene. You can ask the question, what's my energy? What's the relative energies of those doped systems? And because of symmetry, you can get away with fewer calculations, but effectively, this over here, the left one, APDFT, that's the quantum alchemy answer. And that's something that you can get today on your desktop. And that's slightly more accurate than doing NP2 on all of those, if your reference and electron density derivatives come from coupled cluster. And NP2 is something that's going to be next week on your national supercomputer if you have all of it. So from that perspective, the quantum alchemy thing is much faster. And that's the idea. If you have this high throughput calculations, then maybe the perturbative answer is also approximative. Same way you can't afford to do coupled cluster for everything, but it might be more reliable. Here's another application that I would like to point out is where you can maybe see the rigid structure to be relevant. Imagine you have, in this case, a stacked coronine dimer, but imagine you can also think of this as a surface and you want to trap a molecule or be sensitive to a molecule. So here we use the same procedure to predict or estimate the interaction energy. And you can do that as well, in this case with a genetic algorithm, because the search space now is 10 to the 10. And still we can do this with quantum alchemy and then verify later on with quantum chemistry calculations. This, in fact, is the right answer. Now, this is the application part, but I don't want to go too much into detail about the applications, because there's one beautiful aspect of quantum alchemy. As a Taylor expansion is a closed form expression. I can write it down, I can look at it, and I can understand what these terms are doing. And if you look closely, then you find a symmetry. So you all know chirality, the handedness of geometries. And you also know that there is rotational symmetry, translational symmetry, inversion symmetry. But I would like to make the point that you can also show that if you go back to this benzene example, that doping BNNB and doping NBBN needs to be quasi-degenerate. And it's a separate symmetry. It's a tricky one. But it's only quasi-degenerate because this is correct up to third order in the perturbation expansion. So higher orders would break the symmetry. But the difference is usually much smaller than what your quantum chemistry method can resolve. So think about it this way. You start from this molecule over here. And you can now reflect it spatially. You get this one. But now, going from front to back, you replace the boron with the nitrogen and vice versa. So you reflect the nuclear charge. The 5 gets reflected and the 6 of carbon and becomes the 7 of nitrogen. And this is an orthogonal symmetry or orthogonal mirror operation that you can do. I know it takes a while to twist your head around it, so I have some more slides going to the detail on this. So alchemical enantiomers, so two molecules which are different, they differ in the nuclear charges, need to be quasi-degenerate if they fulfill 4 conditions. The first one is we don't want the trivial case, right? So we can just take this molecule, rotate it, you get that one. So we want to exclude that. The second condition means alchemical coupled. And the idea is the way how you increase nuclear charges if you go from your reference to this target is the way you decrease nuclear charges as you go to the left. So this is just along a 1D axis, this is the requirement. And now we inherit the condition that they should be isoelectronic because we're not changing the number of electrons. So the formalism doesn't do it. And now comes the tricky one. Let me read it once, and then we go through the bits and pieces. Where each transmutating atom, so wherever a nuclear charge is changed, is assigned to exactly one subset within each of which evering of nuclear charges results in identical chemical environments. We thought long and hard about it to make this simpler, but sadly, physics happens to be that way. So the easy way to think about it is with an example. This is naphthalene, so all carbons behind the blobs. And now you can have this doping pattern and the doping pattern on the top. Those two are chemically coupled. And what we want is to connect those two. So the easiest way to see it is if you average those two molecules in terms of nuclear charges, you end up at naphthalene. And now the naphthalene has symmetry equivalent sides, namely the green ones, the blue ones, and the orange ones. And each of those symmetry equivalent sides, they need to have a net change of nuclear charge of 0. So for the green ones, only these two sides are changed, and they average out to carbon. The blue ones have these two sides changed, so they average out to carbon. So that's the symmetry requirement. If you don't believe me, you can plug this molecule into your favorite quantum chemistry method. And these are the total energies, which differ by 1 millihartry, in this case for copper cluster. So that's virtually indistinguishable. But you can use that, the symmetry, even though it's approximate only, for example, to accelerate machine learning. Here you can, we have the n-doping of the graphene case. And if you use the symmetry, you can fold this one molecule and the other molecule, the other system, which are symmetry equivalent, onto each other. And you only need half the data that you needed before because you can use the symmetry. And this makes sense, of course, as long as your machine learning model is less accurate than the average difference in energy from higher order terms, which is this red line. You can use the same pen and paper expression, again looking at those two molecules, to find bond energy requirements. That's what you have here. If you do the bond counting on the left molecule and bond counting on the right molecule, then you get an approximate expression on how the bond energies need to be related to each other. That's again a consequence just of the symmetry. And we have tried this for graphene, diamond, all possible substitution patterns with up to 8 heavy atoms. So there's more such rules also for angles that you can get just from symmetry. Now, if you can relate molecules, then you can also say which ones of those need to have the same energy, so you can build chains. Of course, it's transitive. If A has the same energy as B and B has the same energy as C, then I know something about A and C. So I can use this information in order to rank molecules. This is now, again, n-doping naphthalene. There's about 2,300 unique ways of doing that. So you can easily enumerate the space. And what you see here in the plot on the left is the couple cluster rank. And what you get here is the rank just from our symmetry. So that's the consequence, just because you can say this molecule needs to be the same as the other one. And you see that gives quite decent correlation. Maybe more insightful than the correlation plot is this one here. That's the rank error. And this basically shows how often a certain rank error appears. Yeah, question?
Sorry, but how do you rank them if you say that they're symmetrically equivalent? Like,
Because the only thing that breaks the symmetry is the nuclear repulsion. So it's think of it as first you build approximate chains of or groups of molecules that need to be equivalent. And we do this by not only allowing for identical chemical environments after averaging, but also allowing for approximate chemical enantiomers. It goes a little bit more into detail how exactly this is done. It goes beyond what fits on a slide. But the core idea is you first build groups, then you break the symmetry by adding nuclear repulsion. And then you combine this with existing symmetry, with existing constraints, for example, the strict sorting of the stoichiometries, which is the reason why you have these nodes forming in the ranking here. So it takes some effort to get this into a ranking, but the core idea is you use the breaking of the repulsion. Now, if you look at the ranking here on the rank errors, then a perfect method is an L, right? There's a mirrored L, because there's no error whatsoever compared to couple cluster. And on the top, you have something like force fields or bond counting. But for example, also semi-empirical methods from time ago, PM6. And the orange line is what you get just because of the symmetry. So no quantum chemistry whatsoever, just symmetry. So we're somewhere between the old way of semi-empirical methods with PM6 and the new way of doing semi-empirical methods with XTD, just because of symmetry, which means there's a lot of information that you can already extract just from the symmetry and then improve upon in later work. So we applied this to picene. You can take this molecule and now you can de-endope all this about this molecule. And the search space that we looked at is 414 million molecules. You can just use the symmetry again, rank them, and then look at features. So yes, the individual ranking might not be perfect. There will be some rank errors, some ordering errors in the symmetry. But you can get trends. You can capture the dominating trends. Think of it as you get a table which is kind of sorted, and now you figure out by which column somebody else sorted this just by looking at the trends. And you can see that the sorting first goes by that column, so that feature of a molecule, and then later goes by some other column, another feature of the molecule, which means that the first one is the stronger impact, has a stronger impact on the ranking, and the second one has a lesser impact on the ranking. So what we did is take this molecule, go through all those 400 million de-endopings, rank them, and then analyze them. And then we can get rules and also the relative ordering of those rules, how to build a more stable de-endoped molecule in this case. And of course, you can say some of those are less surprising. So if you take 2 carbons and replace this with a Bn, then this makes perfect sense. This is lower in energy, and also that's a total energy, so not as interesting as the relative ones. But then, for example, if you look at this rule, this gives you something about the relative energies, because it says that if you de-endope, it's much more stable if you do so in these inner bonds here rather than in the outer bonds. So this is something that is a consequence just of that symmetry. And I think this is quite neat because this did not require one in any QM calculations, but we can look at millions of systems at once. Now, for the last minutes, I would like to talk about, as last topic, about a way to get around those derivatives requirements. Because getting derivatives, of course, costs time, and chemical derivatives, sadly, are rarely implemented in quantum chemistry codes. So it would be nice to get rid of explicitly evaluating any of those derivatives. And there might be a way to do it. Currently, we can only do it for atoms, but maybe times will change. If you look at the first equation, that's something that we already know from earlier slides. That's just the full-blown Taylor series. And now the problem is that the derivatives, this here, the nth order derivative of the density as you change your external potential, that's something that takes into account all electron-electron interactions. That's the expensive thing to calculate. But we also have delta V here, the change in external potential, which is totally analytical. I can look at this. This is a closed expression. So the idea is, can we, similarly to what we had in an earlier talk today, squeeze space, change the, make the coordinates be a function of lambda, and then move those derivatives from the electron density to a change in the perturbing potential. So the idea is first you do chain rule to split this up, and then by partial integration, you move, you remove the derivative from the density and make this part of the external potential. And it's a lot of derivation and mostly index keeping. But if you do this in 3D, then what you get is something like this. You get one object that I'm not going to show you because that's about 2 slides and quite ugly. This is ugly but analytical. So I can easily evaluate this and quickly evaluate this. And here we have the density of our initial external potential. So the reference molecule where we start from, which is great because I only have to do this once, and then I have to evaluate this analytical element here. So I don't need any explicit density derivatives. Now, of course, there is no free lunch. The problem is you need to know your electron density really, really accurately. So that's currently our main problem, and I will talk about the limitations of the practical side of things, in particular in the context of basis sets in one of the later slides. So let me show you some numbers. If you look at the left first. So this is for the hydrogen-like atom, for which you know the exact answer and where you can get your derivatives with the change of nuclear charge quite readily. And you can either do the exact solution that you know, or you can do this, what I showed on the previous slide for this particular atom, and you see even for substantial changes in nuclear charge, this goes up to 5. This gives a perfect correlation between those. They agree up to machine precision. Now, where the problem comes into play is the moment we start changing 2 things. The one thing is we add more electrons. Now it's a multi-electron problem. But the other thing is, because there is no analytical closed-form solution for that, I also have to use a basis, a finite basis, to expand my electron density. So right now, it's not entirely clear which one of those makes the largest problems. But there's a good suspicion that this is dominated by the basis set restrictions. So what we do here is still an atom. You go from one nuclear charge, Za, to the other nuclear charge, Zb. And then what the heat map shows is the error that you make in using the expression from the slide before. So the one where we don't use any density derivatives at all. And you see, I don't know whether you can see it on the projector, but every time you are exactly at the integer nuclear charge where the basis set has been parametrized for, then you have a blue line here, a region of very low errors. Maybe I can enlarge this a bit. So every time that happens, what you get is some range where this is very accurate. The moment you go to non-integer nuclear charges, this becomes less accurate until you reach the next integer again, where you have a parametrized basis set. So this is very likely a problem with the basis set. And the other aspect to keep in mind is if you start from nuclear charge of 1 and you increase your nuclear charge, then of course this means you pull the electrons closer to the nuclei. And standard basis sets, of course, have no functions in that space. They're not that tight. So, of course, you have to find a way to respond to this. So, from that perspective, it's clear that, that there are some numerical aspects to take into account in this way, but it's promising in a sense that it would allow to get rid of the density derivatives in an explicit calculation, if we can sort out the technical limitations. Speaking of limitations, imagine you want to try it out. So what's the issue and why is this not readily available? So the first problem is both energy and density derivatives are hard. There's hardly any quantum chemistry code that gives you those things readily, except for maybe the first order, which is just the electrostatic potential at the nuclei. In the Hamiltonian picture. So how can you get those derivatives? Well, of course, what always works is finite differences. It's very expensive, so you change your nuclear charge a little bit and you calculate how does my density or energy change. And that has some numerical instabilities. That's what we did initially for some proof of concept work, or which you can do with arbitrary precision, at least for Hartree-Fock. And that's how we got the convergence plots that I showed in the beginning. You can use Hellman-Feynman derivatives. That's very much limited by the fact that the basis set is not complete. So the gradient sometimes even points in the wrong direction. That's the reason why for forces, we have to evaluate the Poulet terms to actually get the proper gradients of the forces in quantum chemistry environment. So Hellman-Feynman is, at least as long as you're far away from the complete basis set limit, no help. For Hartree-Fock, you can do a couple perturbed approach that gives you the first few orders, but is fairly tedious and doesn't work for higher level methods. You can use the conceptual DFT picture, so the susceptibility. We talked about that in the first workshop. The susceptibility is related to the second order derivative of your energy in that regard. So you could use it, but that's very memory hungry because your dimensionality of this tensor increases every time you add a new derivative. And there is no post-Hartree-Fock answer to this. What I think is the way forward is automatic differentiation. So with the advent of, or with the boom in machine learning, more people are also looking into ways how you can do quantum chemistry in a differentiable way, which is brilliant because this means you don't have to sit down and derive whatever derivative needs to be evaluated for your favorite functional. Again, for the third order mixed derivatives of spatial and nuclear charges, nobody's going to do it. But this way, you can actually do it, and there's a few codes that can do fully differentiable DFT, Hartree-Fock, and coupled cluster. And they recover this way the same derivatives that you would get if you were to do the coupled perturbed approach or the lambda iterations from coupled cluster. So this you can use. There's a few codes, one of which DQC for differentiable quantum chemistry. They even did alchemy that way directly with geometry relaxation. So that's a really neat thing. It's a little bit niche, so but I think that's the most promising way how to get those derivatives with reasonable overhead.
Does TensorFlow have this capability?
So TensorFlow is what DQC uses, I believe. So Quarks is quantum chemistry with JAX, which is a library by Google for automatic differentiation. And they have this beautiful logo, I had to show it. And the DQC uses TensorFlow, I believe. But it's let's say currently those codes are in the stage of proof of concept, of showing that you can actually do it and that you do recover the same thing as the much more complicated lambda iterations or couple perturbed approaches. And this, I think, they could show. You can check this with finite differences. Even for mixed derivatives, they do get the correct energies. And of course, right now they do the full iteration, so they're very slow. But there's no need to that. You can just do the iterations, the SCF, with your quantum chemistry code that you use already, and then just plug this into the differentiable code, do one step, and then you get the same gradient. So I really think that automatic differentiation is the way forward, not only for these kind of derivatives, but for arbitrary derivatives. Now the catch is that the Gaussian basis set is not terribly helpful for all of this, because you can imagine you not only have to be able to represent the electron density of a system in this basis set, but also the change of the electron density. The derivative needs to be representable as well. And there is another less obvious problem. If you go from, say, N2 to carbon monoxide, then where your Taylor expansion ends up with is not carbon monoxide in the basis set of carbon monoxide, but in the basis set of N2. So as long as you have a basis set that is tailored towards a specific element, then of course you don't recover this exactly same number that you would get in the different basis set you would choose for the target molecule. So of course in the complete basis set limit this should not exist. But part of the problem is that the density derivatives converge much more slowly than the energy, so you need much better basis sets in order to describe that. But that goes into the direction of what I mentioned initially. If your reference calculation is of better quality, then you can cover all the different target systems.
Now, question.
Yeah, sure.
Could you make your basis set Z-dependent? You can make a universal Z-dependent.
Funny you should say that. I would actually argue that the basis sets should be system dependent. That's one of the things we're actually trying out here. So what if you have your system with nuclear charges and coordinates describes the Hamiltonian, but maybe it should also describe the basis set. If you pick, as you change the coordinates and as you change nuclear charges, then the basis set coefficients and of course the basis set centers, they should move alongside that. And then of course you would generally solve this kind of problem. I mean, yes, you can get Poulet terms which you have to deal with, but there's standard solutions for this problem. So in this way, I think that's probably the best way forward to fix this basis set problem. And just as a caveat, I mean, it's I mentioned this, but I think it belongs to the limitations of what you can do. You can only go to some finite radius. You can't go arbitrarily far. But I did show you some examples, the C20 case with a few million molecules, or the stacked coronine case with a few billion cases at once that you can treat just perturbatively. And going back to the question from Trine, so not all systems are made equally. That's correct. So if you do the perturbation approach from something highly symmetric, then the convergence is faster. I'm not entirely sure why that is, but that's just something that we see in many applications. So with that, I hope to have shown you that with quantum alchemy, with this perturbative approach, by adding more orders, you can get something which becomes more accurate in a systematic fashion. It's uncontrolled, sadly, so you don't know how accurate you are when you add another order. But because you have something which gives a closed expression, you can actually look at the pen and paper expression of how the relative energy between different molecules look like, and maybe draw some conclusions for that, be it for machine learning models or for design applications or for approximations that you use model creation. There's different avenues that we currently pursue in order to figure out how to get those derivatives, which is, I think, the main limitation currently. We know how to do this in about 5 or 6 quantum chemistry codes, but chances are that many others could do it. So that's not the issue. But the beauty of this is that eventually, once you have the technical things sorted out, your perturbation scales with all those different combinations of nuclear charge changes that you can have in your system, on your surface, or whatever you're looking at. So with that, Simon and Anatol are the collaborators on this for most of that. And those are the 4 core papers, depending on what exactly you're interested in. So thank you very much for your attention.